Okay, welcome back everybody. We're moving on to section 14.2, which is called linear systems and flows. So we're still sitting inside of ordinary differential equations, except now we're going to start to talk about, in particular, linear systems and or flow systems, because these are in some sense the two that we know how to solve very easily. Once you get outside of this idea of systems, then it's pretty hard to solve some of these. So we'll just start with the definition of linear. A linear system of ODEs. The word linear comes straight from linear algebra here. So you'll recall in linear algebra, we're dealing with vectors and matrices. And so a linear ODE, in particular, if it's a system, it's really just a matrix. Okay, so we're going to consider A as a matrix. A of T is a matrix, which possibly evolves over time. Right. So A is a matrix which evolves over time, and it just acts on the vector x, and whatever the image of the matrix on the vector is, that's how x changes over time. So that's what a linear system of ODEs is going to look like. It's a system because I'm working with a vector here and a vector here, so we can reinterpret the vector as each entry in the vector is its own little one-dimensional particle that's possibly influencing its neighbors through the action of the matrix A. Now I want to make a slight comment here because I don't know if I like the way that Colin wrote this. This should also be possibly added with a function that depends on time, f, a vector. Really, this is a vector. This is a curve. This is a curve which depends on time, right? Because it's a vector which depends on time. But this is a forcing. Okay, so we could possibly add a forcing. And this still stays linear. Okay, so the addition of a forcing still gives a linear ODE. So it's an example of a forcing. If this were describing the interaction of electrons, if I decided to, maybe the electrons are just in a wire, they're moving through a wire. If I decided to move a magnet back and forth near the wire, that's a forcing, right? So that's going to apply a force to the electrons. It's going to influence their velocity, and that velocity is going to be independent of the electrons themselves, right? It's just going to be forced into the system. But that doesn't make the system nonlinear just by adding a forcing. So we want to make sure that we have that sitting around. Okay, if it's not one of those two situations, then it's called nonlinear. So I can have a matrix on my vector. I can also have the matrix on the vector, and I can add a curve into the system. Those are still linear. Anything else is nonlinear in the sense that if instead it weren't a matrix acting on x, it would just be like a function of, I shouldn't use capital F because I use that for forcing, maybe a vector field inputting x and time, and as long as the vector field can't be represented by a matrix, that would be like the nonlinear setting. So let's look at a heat system really quick. So we have three particles with temperatures, U1, U2, and U3. They're going to interact with each other according to this interaction. So the change in U1 depends on some negative constant on U1 and a positive constant on U2. Change in U2 is a negative constant on U1, negative constant on U2, and negative on U2, negative on U2, positive on U1, and positive on U3. And then the change in U3 is negative on U3 and positive on U2. We can actually represent this as a linear system of ODEs by grouping things into vectors, right? But in particular, what I want to point out on the right-hand side is every case of U1, every case of U2, and every case of U3, because this is how we're going to start to interpret these as matrices now. If I want to represent this as a vector U, which equals the change in the vector U equals a matrix acting on the vector U. If I want to know what this matrix is, it completely depends on what sort of multiplication is happening to each U in each line. Okay, so that's why I circled each of them. The components of that matrix depend on the multiplication which is happening to each U in each line. So what do I mean by that? What I mean is that the matrix M is going to be the interaction of U1 on U1, the interaction of U2 on U1, the interaction of U3 on U1, and so on. So this would be the interaction of U1 on U2, of U2 on U2, of U3 on U3, etc. So what I'm going to look at now to develop M in this particular system, M from that system, I say what interaction does U1 have on U1? Well, it's right there. It's negative K1. That's the interaction of u1 on u1. What's the interaction of u2 on u1? It's positive k1. Okay. What's the interaction of u3 on u1? Well, there isn't one, so that's represented by a 0. What's the interaction of u1 on u2? So I have to go out of my way and search for a u1 in the second line. It's k1. The interaction of u2 on u2 is negative k2 and negative k1, so negative k1 minus k2. And then the interaction of u3 is a positive k2. The interaction of u1 on u3 is what I'm looking for there. u1 doesn't exist in u3, so that's a 0. The interaction of u2 on u3 is k2, and the interaction of u3 on u3 is negative k2. So I just wanted to bring that up. This is how we would find a matrix if we were given an ODE that in fact is linear, right? If I can represent it by a matrix, that means that the only influences that they're going to have on each other is just multiplication by a constant, right? So u1 can influence u1, but it can only influence with a multiplication of a constant, multiplication of a constant. You'll notice every influence is a multiplication of a constant, and those constants end up exactly in the matrix there. So if I scroll down a little bit, hopefully this matrix shows up, and there we can see it. So they're calling it L, they're calling the matrix L, but there we can see that we have the same matrix that I just developed from before. And so I can represent this system as in fact, a vector u, which changes over time, the matrix acting on the vector u. Okay, so that's how we would maybe develop a matrix out of a system that we're given. And then we're going to move on to this idea of flow. So the idea of flow is a little bit broader. Here we're going to have a vector field, but it's not going to depend on time. Hopefully everybody sees that. It doesn't explicitly depend on time. Spell a little better. Doesn't explicitly depend on time. What I mean by that is that this is not v of the vector x comma t, okay, in the sense that if I forget about the vector, the field itself does not evolve in time. It only depends on x, and x is allowed to evolve in time. And what does a flow system actually describe? A flow system describes this word. It's called advection. Okay, you've probably heard of convection, right? It's what happens in your oven when you turn the fan on, and actually it happens even if you don't turn the fan on. Convection is the movement of a fluid through itself, traditionally via some pressure differences. Advection is the motion of an object embedded in a fluid. Okay, so if I place a rubber ducky in my tub and I drain the tub, the water would start to whirlpool and start to near the drain. You get a little vortex near the drain. The rubber ducky is the object which would be embedded in the fluid, and the object is going to trace the path of the fluid as well because it's being pushed by the fluid, but it is not the fluid itself. So an object inside of a fluid. The fluid, so the velocity of the fluid is described by the vector v. Okay, so this now corresponds to, now that we know how vector fields look, we can think about, a big old field of wheat. We look at all the directions the wheat is pushing in. Now replace that wheat with water and say that those directions are the directions the water was moving in. If you put a rubber ducky on top of the water, this flow equation is what describes the behavior of the rubber ducky through the water. Okay, so if I were able to solve this equation, it says I'm putting a particle or an object into my vector field. Where does it end up? And so maybe I'll just draw really quick. Suppose I have my nice little vector field. Suppose we have these nice little curvy vectors. And maybe they start to diverge up here. Okay, so there's my vector field. It doesn't look too terribly smooth, but that's okay. If I start my object right there, it's going to flow, and then maybe it spreads over here. That would be the flow of the object in a vector field. And that's what this equation describes. So we start with the vector field. We basically say, I'm going to put an object inside of it. Where does it go over time? And these are somewhat easy to solve. It depends on the structure of V, how easy these are to solve. And that's why we look at the following case. We look at the vector field minus y, x, and a quarter z. Then I can check the curl of that vector field as well as its divergence. And we can, in fact, solve this because it's linear in the sense that, each term is only multiplied by a constant, right? I'm multiplying by a quarter, I'm multiplying by 1, and I'm multiplying by -1. We can solve this and we recover the formula cos t sine t and 1/2 e to the t over 4. If I were to plot this, if I were to plot this, then what we can see is through the vector field, given my vector field, this is the vector field we used a long time ago, except for the 1/4. In the xy plane, we have this rotation, and notice cosine and sine as our solutions to this vector field give us a circle. So we have circular, the rubber ducky goes circular through the xy plane, and yet it moves up. Green is where we start and red is where we end. It moves up over time in sort of a helical path through the vector field because we have this notion of a positive divergence, and in fact a positive divergence in the z direction. So this is saying we're being pushed in the upwards direction by our vector field. So that's basically the flow of the rubber ducky inside of this vector field. Okay, so in fact, here in exercise 14.2.1, it says, show that the example above is linear by constructing a matrix such that x dot equals ax. Let's do that right now. So we're going to call the vector x, this is going to start to get a little confusing, but the vector x we're going to call x, y, z. And so if I put a dot over those are dot x, dot x, dot x, dot y, dot z. And if I'm considering the equation, vector equation, flow equation, x dot equals v of x as a vector, there's v of x, and so I have x dot y dot z dot equals negative y x 1/4 z. If I want to construct my matrix, we'll recall I'm asking the question, how much does each term, what is the coefficient on each term's influence on x1, x2, and x3, which in this case is, I suppose, x, y, and z. So how much is the x influence on x dot, if I construct my matrix L? What is the x influence on x dot? It's 0. What is the y influence on x dot? It's -1. What is the z influence on x dot? It's 0. What is the x influence on y dot? It is 1. What is the y influence on y dot? 0. What is the z influence on y dot? It is 0. And then finally, the x influence on z dot is 0, y influence is 0, and the z influence is 1/4. That looks like the Jacobian. It is in fact the Jacobian, so that's one way to think about these flow systems. So long as they are linear, we recover the Jacobian as our matrix. So that's another reason why the Jacobian is kind of an important matrix to keep in mind. But that's only in the case where we're actually a linear system. Okay, so there's L, the matrix for which this system is linear. So if I were doing this next example, I'm going to scroll down now, or this exercise right here, show that it's linear by constructing a matrix A such that x dot equals ax. I constructed the matrix L instead, but this L exactly gives that relationship that we're looking for. We're going to move on now to what's called gradient flow. So this is a very specific kind of flow. Gradient flow is flow specifically for a curl-free vector field, i.e., we'll recall that curl-free vector fields were the same as vector fields which equal the gradient of a scalar field. So gradient flow is specific flow when our vector field is now a gradient of a scalar function. And these flows are really, really nice because what they describe is these describe the flow, I'm going to say up a hill. So if I have a scalar field, which is some sort of hill, right, the flow, if I place an object in here and I want it to make its way to the top of the hill, that flow up the hill, maybe I'm on a ski lift basically, on a ski lift or whatever, that flow is perfectly described by this differential equation. Okay, and up a hill is not maybe the most important thing to measure. It's in fact down a hill. That's really important to measure. This is called gradient descent. And all I've done is I've added a negative sign in front of my gradient, and this describes the motion down a hill. And the motion down a hill is incredibly important in all sorts of mathematics because it lets us minimize things. If I drop a ball on a hill and wait, it finds a minimum. That's the number one reason why we care about these gradient descent algorithms, is that if I drop a ball on a hill and wait long enough, I don't necessarily know how long I have to wait because I don't necessarily know how big the hill is. But if I wait maybe 500 months, a really long time, the ball probably found a minimum, right? And so if we compute the solution to a gradient descent system of ODEs on a computer, and we compute the solution at some future time that's really far away, I've almost surely found a minimum. And why are minimums important to find, so this isn't a very high dimensional system, right? So I could have 10,000 dimensions, and if I compute this algorithm, which approximates gradient descent on a hypothetical hill, and wait a really long time, then I've minimized a function. I've minimized the function f, actually. I've minimized the height of the hill. And that's really important because if I'm an industrial engineer or something, and my boss asks me to minimize the cost of producing some widgets, then all I have to do is run a gradient descent algorithm on my cost function, and if I wait long enough, then I find exactly the amount of money to spend on each of the x's could represent how many of each part for my widgets I need to buy. I can find the minimum cost. I can find the amount of each part I need to buy to minimize the cost f using gradient descent. But I can also minimize all sorts of other systems. So like in physics, we like to minimize the energy of a system, right? So if I take my protein and I ask what configuration should the protein be in, I'm going to think about F being the energy. It's the potential energy of usually the electrons in the protein, and I'm going to compute gradient descent on that, wait long enough, and it's going to tell me the position the protein exists in, which minimizes its energy. And so then all of a sudden I know the shape that the protein takes. So this is basically, if you can take one thing out of this course, it's probably this right here. Gradient descent is all over the place. You can't really avoid this if you go into any sort of computational job, even computational chemistry. But if you're an industrial engineer and you're using computers to minimize costs of some things, like this is all over the place. If you go into the stock market and you want to minimize your loss probability on a sequence of stock trades, you use gradient descent. Okay, it can be a little bit more complicated than that. We actually have slightly better algorithms, but this is definitely the starting point for all of them. But anyway, I think that's all I have. Yeah, that's all I have. So we're going to move on to PDEs next week, or I guess the next section, which is after your next homework. So yeah, we'll talk about gradient descent and some more things in class. Anyway, that's all I have. Bye.